let us summarize what we have achieved. And in fact, we have constructed a solution for our differential equation. And it is most conveniently formulated in terms of polynomials p and q. And notice that in this case, these polynomials are of the second order. And this is because our initial differential equation was of the second order in the derivatives. So, and the solution is represented by this formal integral. And the only requirement is that, first of all, the contour integral which defines the Laplace transform of our solution is convergent. And in addition, we have to require that the contour integral of a total derivative should vanish. And of course, this can be achieved by several ways. So the most trivial of them are that either, say, this function vanishes at both ends of the contour as long as it is not closed one, or the contour is closed and this function is single valued and takes its value after the contour is passed. So this is the requirement for the solution. And let us now try to apply this technique for the area equation. So as you remember, it's of the following form. And as we have discussed in the very beginning, for this equation, only non-zero coefficients of this 6 is a2, which is equal to 1, and b0, which is equal to -1. So this means that p is equal to t squared and q is equal to -1. And we can write down explicit expression for z. So z equals factor -1, which can be omitted, and z equals exponent of integral p over q dt, which is just integral of minus t squared dt. That is exponent of minus t cube over 3. So finally, recalling our definition of the Laplace transform, we may write down for y of x the following result. And so apparently we have constructed for now it's a formal solution because contour is not defined, but still we have constructed a solution to our area equation, and let us now try to analyze it. So first of all, it's evident that this looks like only one of two linearly independent solutions. And of course, this apparent paradox is resolved by the fact that we actually have a freedom in choice of contour C. And let us see what kind of contour should or can it be. So this is a complex plane of T. And most conveniently, of two options discussed in the beginning of how to make this integral of the full derivative vanish, we will choose the simplest one when the contour goes to infinity and the integrand just trivially vanishes. So we need to analyze which are proper directions in which this vanishing of this function happens as fast as possible. So in fact, these directions are like that. And it's easy to understand that, for example, consider this direction. It means that basically t is real and goes to plus infinity. And in this case, expression in the exponent is also real and quickly goes to minus infinity. So this integral converges quite fast at this direction. So, and in principle, we can of course try several ways to define the integration contour. So apparently, the contours which are most convenient are shown on this figure. Let us briefly discuss what does the most convenient mean in this case. You remember that in the previous discussion, we have considered the solution of the following form. This is, of course, still a valid solution, but it is not particularly comfortable to work with this kind of integral. Why? Because it's, and especially at large x, large positive or large negative, it is not very convenient to deal with this type of representation. Why? For obvious reason that this integral has very poor convergence properties. It does converge, but in fact, there are strong oscillations in this integrand, and especially if you want to calculate it numerically, it's problematic, and at large values of x almost impossible. And this choice of contour is much more convenient because in these directions, which are dashed here, the expression in the integrand vanishes very quickly, and of course the integrand sits on a narrow region of T. And this specific choice of contours, it can be dictated by many reasons, and one of them is to guarantee convergence. And of course, one of the crucial, another crucial ingredient is that we can, in principle, write now several solutions. Say y I of x equal to integral over gamma I, exponent of x t minus t cube over 3 dt. And again, someone very naive can think that, for example, he has 3 linearly independent solutions to the second order equation. Of course, this is not the case. And although, in principle, each of the integrals represents some different function, in fact, as the structure of the complex plane dictates in this case, as there are no singularities or cuts for finite values of t, it is obvious that sum of the integrals over all of the contours simply vanishes. So in fact, although these are 3 formally different solutions, of course they are linearly dependent. But each of the 2 contours provide a set of 2 linearly independent solutions. In fact, in your homework exercise, you will have to provide an explicit understanding that, for example, in particular, we know that this function, which is just area function, is also one of the solutions. And it's relatively straightforward to figure out to which of these contours, or possibly linear combination of them, does the area function correspond. And this will be one of your home exercises. Let's finish with this brief introduction and go on with solution of some less trivial differential equations.